minus 4x minus 1 equal to 0.
Shouldn't? There's not.
No.
Oh.
This is
I have an idea for the set one.
Oh, good.
You find it.
No.
Wait, do you want to show us the geometry one?
Give
First?
me 16, 15. That's not possible, right?
No, it's not. There's only 17 because down.
No, this is Sunday. This is next point.
Okay.
Which is super annoying.
Like, which part can I roll out? Just like.
Oh, you can rub out everything now.
Okay.
Yeah, just explain the question again, so people know what's going on. Exciting times, people. Exciting times.
Now?
Yeah.
What's exciting about this?
Like the beginning of the new era after AIMO era.
This was like after I finished the AIMO course.
I mean, like, this is your last day AIMO, right?
Yeah, it is.
So we're gonna make a run for the AIMO. And so we call them up so that we can now teach you the same stuff.
I want to make it into that thing. I think I did pretty well this year. I am sure. Wait, you have to do one the AIM.
For the summer camp, there's a summer camp. So like, not the selection school. That one for the summer school one, you can go just. It's based on your AIMO. So
Just don't screw up in any testing or.
Yeah.
Well, so far I haven't screwed up anything. Yeah, except for my math instrument.
it's multicolored.
What do you get?
Oh.
Like really trash.
Whoa, it's darker now. It's like so it's just running out there.
Yeah, so we're assuming that the triangle has the property that the heights all meet at a point. Okay.
Yep.
Inside triangle.
So I guess this triangle has to be acute.
Yep.
But we don't need to worry about that. We just take that for granted. Yeah. Whatever the triangle is, it has this property that the heights meet at a point.
Yep.
Okay. And then we're trying to show that basically, maybe I can phrase it another way to make it more interesting. But basically showing that if you had a billiard ball bounce off the wall in this trajectory, right?
Yeah. It would
It'll bounce off that way and it'll bounce on forever in that cycle, right?
Yeah. Oh yeah.
Okay.
Yes.
So we're trying to show this angle is equal to that angle.
This angle is equal to this angle.
Yeah. And then
And these two are equal.
Yeah.
So we can just like start by setting one of them as alpha, right? And beta, because that makes it easier. So as some of you might have noticed already, this is a cyclic quad because these are both 90 degrees. So then we can use the theorems to make this alpha and beta. And we have that this because given that this is alpha, this is 90 minus alpha.
Yeah.
And this is 90 minus. Wait, sorry. 90 minus beta, and then check my sheet. Okay. Oh yeah. So you have that this is 90 minus alpha.
Yeah.
So this
Vertically
is
opposite.
vertically opposite 90 minus alpha.
Wait, how do you know it's not 90 minus alpha?
Because
9 degrees. So you know it's alpha because it's cyclic quad.
Yeah.
and then given that obviously this is 90 minus alpha, right?
Yep.
So then because we know this is a cyclic quad too, right?
Yeah.
No, not the angle, but the
So this is a cyclic quad. So this is equal to this, so this is also 90 minus alpha. Right?
Yeah.
And then so since then this is also alpha, so these two are equal.
Yeah.
Wait, why
So-
is that not? Wait.
Do you want me to? Okay, yeah, you play with
Yeah, so and it suffices to just to show one of those angles are equal because it's arbitrary. So if you just drew it another way, it would show the other two are equal as well, right?
Why does that Oh yeah, okay. Yeah. Cyclic quad, yeah. Yeah. And then once you know that, then you're done.
Yeah. Wow.
Yeah. Yeah, so it's a nice little angle change problem, yeah. So the context of this problem is kind of interesting, okay? So if you have a triangle, okay, and you have a billiard ball, right? And you bounce it around, okay? Right? So in this case, it's periodic, right? It just keeps repeating.
Assuming there's no friction.
Yeah, I mean, it's not really a ball, it's a billiard point. Well, yeah, so it bounces around. And the question is, for any triangle at all, right? Does there always exist a periodic path?
Yeah.
You know what I mean? This is period 3, I guess. But so.
Well, I guess you can like, given the altitude points, if you have like any triangle has an in circle, which means it has an in.
So obviously this is a solution to that problem when it's like acute angle, right?
Yeah.
When it's obtuse, so this problem is an unsolved. Well, I think it was at least unsolved in 2012. I'm not sure. It's probably still unsolved now. Yeah. This is an unsolved problem. If there exists a trajectory that repeats, like arbitrary triangles.
Oh.
And the video, I saw a video and it said like it's known up to like 100-degree angles. Like if the triangle has an angle 100 degrees or less, then they know there always is something like this.
100 degrees? I should 90 or 100.
So they did it with a computer, so that's why they said 100. Just so if the triangle has the biggest angle is less than or equal to 100 degrees, then they sort of know you can always find some trajectory. Yeah. So I guess I'm telling you, like this is also meant to make you feel better. Sometimes like there's problems that look like you should be able to solve, and they're actually not solved yet by all of mankind. You know. So that's something that could like in your test. You know, like I'm sure every question that you did on your test was at some point an unsolved. You know, like in some form, right?
Oh yeah, caveman.
Yeah, but I guess a lot of you didn't have this. The cheering up factor isn't really needed. Yeah. So did anyone get the sets question?
Did I get this question?
I have an idea, just haven't pursued it after my final.
Oh, okay, what's your idea?
For any like given for like every set, including the empty set, like from the empty set to like all the so if you have like all the sets that aren't like that they are the union of themselves and the like and the empty set for all the sets like for the union of all those sets from like for the set with that's the union of all of those between the empty set and that set like for every like set there's the complement of that set
complement.
Or like all the sets between there. Every combination of the sets between there is. So like, if you have like sets as like A, B, and C, right? And then you have the empty set, then there's like. Then everything in between this like exists.
Everything in between exists. Yeah.
So, right. So then, like, if there's an A, there's one that doesn't have A. So like.
Okay.
And then, since once you do that,
well, that's a good example because that's an example of a union closed family. Isn't it? Yeah. So it's a.
Not A B. Well, wait. Is A? Oh yeah, it is.
Yeah. So this is called. Yeah.
Wait. Hang on.
Yeah, so I'll remind you the problem. So the problem, you remember the problem? You have a family of finite family of finite sets that's union closed. That means like anytime you have two sets in the family, the union is also another set in the family. And we have at least one non-empty set that contains one element. Okay? And we want to show that that one element is in half of all the sets.
You need these ones as well.
Yeah.
Yep. So
you need because you need A union C, right?
A union C.
You need A union B.
Yeah.
And then you need B union C.
And then you need A, B union C.
Yeah. Right.
If you do it like A, B union A, then that's just A, B again.
Yeah. So this is an example of something that satisfies this property. Yeah. This is actually, I guess you could think of it as the power set of. So this family of sets is the power set of ABC. Yeah.
Yeah.
So it's a set of all the subsets of ABC.
Yeah.
Yeah. So you can see that anytime you take the union of any pair of sets, it'll be in here somewhere, right? And that's the empty set that has nothing in it. Yeah, I guess we're assuming A, B, and C are different things. Well, if they're different things, then we have what, like this number of sets. If they're the same thing, then we have one set, two sets, the empty set and the one element set, right? Because like we don't, if they repeat, then this is just the one, like, you know, A and C is the same as A, is the same as C, yeah? But we're assuming they're all different things. Yeah, and so notice how like C, if C was 1, the thing we had, right? That's in half of all these sets, yeah? Because there's it's in 1, 2, 3, 4, and there's 8 sets.
Yeah.
Right? Yeah, so one way to approach the problem is you can think of this. So if you take you take the finite family, right? And you take any subset, let's not use S, X in the family, yeah? Consider like what you get if you do X union 1, right?
Mm-hmm.
You see? So basically X either contains 1 already or it doesn't, right?
If it does,
If it does,
it will.
yeah. So if it doesn't, then that one will, right? So that's kind of like there's one
for all sets that don't contain for all other sets that do contain 1, there exists a set that's like without the 1.
Yeah.
Yeah.
So there's basically like this. It's like it's 1-to-1 between the ones that don't contain 1, and the one that do contain the 1, right?
Oh yeah. Does
that make sense?
Yeah.
So
it wouldn't be half if there is another one that.
Yeah. Yeah. So that's another question. If you're interested in this question, you can think about what happens if you assume there were 2 elements in that set instead of 1, right? Okay.
Would it matter?
The argument's very similar. Okay. So the question is, what if there is a 2-element set? Yeah. I guess that'd be homework if you're interested. Instead of a 1-element set, can you show that? I guess the question is slightly altered. So can you show that at least one of the elements is in half of all of the sets?
Wait, why wouldn't it be both?
I don't know. Maybe you can ask that question too. So maybe can you show one or both elements in half of all the sets? Yeah. Yeah.
I feel like there should be like, it would be in the like AIMO. It would be pretty funny if one of the if the question dies, because this time we asked about like on this year how many plants there were. But
How many what? Plants.
Oh yeah. They should be like prove that on this year there's like 192 plants. I don't know, everyone would have been like screwed because that was like really hard to like use to prove. Like everyone just did it by like observation.
Yeah.
How do you do it by induction, anyways?
I can show you that sometime later.
Because like I don't even know what induction is.
Oh, okay. We can definitely go through that.
I didn't eat. Oh,
so maybe we should add some number theory at some point.
Yeah.
Number theory is all induction. Lots of the proofs. A lot of the proofs.
All contradictory.
Because I mean, that's what induction is. You have numbers.
Yeah.
Count up. Okay. Anyway, so, yeah, and so this problem actually is another example. So it's a simple looking problem. So the question in general, okay, if you just had that family of union closed sets where one of them was not empty, right? We don't know how many elements it has, okay? But it's finite, right? Because the question says all the sets are finite.
Yeah.
Is there one element right? It doesn't have to be in that set, but is there one element at all that's in half of all the sets? Yeah, that's unsolved as of like 2012 at least. Okay, so yeah, so I guess part of it is to kind of get a bit of an intuition for the difficulty of problems, and you might wonder why this is unsolved and something that looks, I just made the 2 and it's easy to solve, or like, and I think it gives you an idea of sort of where maths can go, that's sort of not just competitions are problems that are like man-made in some sense, or maybe they did come out naturally in some research area, and then people thought it was nice, so they submitted it, right? But like, you go in there knowing there's an answer. These ones, they kind of look the same, but you don't. So, and then like we were talking about millennium problems, right?
Oh yeah, these ones. Wow.
These aren't millennium problems, right? But $1 million isn't as much as it used to be. I'm sure you'll get at least $1 million if you solve either of those problems.
Which two problems?
So the one, the set one, and the geometric, the triangle one.
But he just solved them, so does he get $1 million?
Oh no, the general version. So like he'd solve for acute triangles. So if you had like an obtuse angle triangle, it's more than 100 degrees. Here's if you have a set that's more than 11 elements. It's already unknown.
That's just a millennium puzzles.
There's like 7 of them, right?
It's like Yu-Gi-Oh! The millennium puzzle.
There's like something about fluid dynamics or whatever, I know.
Millennium puzzle?
No, millennium problems.
Okay, so now we're into geometry. Yeah, so I was thinking if we're gonna go through this, do you want one of these books just dedicated to the geometry?
Yes.
I would have one. I don't need.
Yeah, I need a book.
Thanks.
Book. Catch. Oh, Sean, you should get out more. No. Okay, sorry.
I need one?
You can have one.
Yeah, whatever. I mean, after all, it's free, right? It's free stuff.
Yeah.
I still need one of that. One of those.
I'll bring it next week. I don't need one of those. I'll bring it next week.
I mean, this is just to keep it organized, so you can keep all your homework in this book. I'm really hoping to get like pretty far into this book, so if some people are falling behind, you might have to catch them up, or like whoever's not behind gets to catch the people who are further behind up.
This is really cool.
Yeah, it is good value anyway.
I mean, it's surprisingly cheap.
Yeah.
Yes, you get this from China, right?
No, this
Like-
is from Office Works, but like,
Really? It's like the one from.
but
China.
I'm sure the origin was China.
Because like this one's expensive. So you can press this one in there. Like,
I'm not trying.
Ah.
Yeah, like a lot of them do have. This.
Yeah, I was hoping to verify that they worked at some point as well.
usually do, yeah, it worked with this.
But after using it for like a million years, I don't think it's gonna work.
So
Because you'll be like, I don't know.
I have 30%.
Huh?
I have 30%.
30%.
30, yes.
Oh, it's so good. As long as it works, it's so good.
It will look also relaxed. It has that.
So entire book dedicated to geometry.
Yeah.
I see. This is
Maybe we're gonna have another one for algebra when we start algebra. I have plenty of
what?
books.
No. Oh yeah, sure.
You can even call it Geometry Revisited.
Revisited.
I don't know why you call it, but okay.
Well, it's the name of the book.
So basically, I'm plagiarizing every single book.
Yeah, but it's funny because I never visited it, so I'm just visiting it. Just Geometry Visited. Yeah. So the very first thing was the extended sine rule, right?
Okay, what? Oh yeah, you mean like
Yeah.
2R thing?
Yeah, it was like sine A on A, and I want to use this to give you an example of how I want to go through this book. Yeah.
Are you sure isn't it A over sine A?
Maybe it is.
Yeah, it is A over
Is
sine
it the other way?
Yes, A over sine A. Because like
Is it A over sine A?
Yeah, otherwise it's too small.
Yeah, sure.
So if these are the sides of the triangle, And these are the angles opposite the sides. Is it 1 over 2r?
No, it's just it's just 2r.
Oh, you put it the other way around.
It's just 2r. Like this is like the proportion
It's just
2r.
yeah.
Because for the sake
Oh,
of convenience,
okay.
it's just like the sake of 2r. R is like the radius of like the second circle, which is means like this is basically like the diameter of the second circle.
Wait. What's the extent of sine?
This is it. So you have the sine rule, right?
And this little bit.
And we're saying they're all equal to the twice the circumradius.
Okay.
Yeah. So circumradius is just the radius of the circumcircle. So if you take a triangle, right? That's A, and this is little a. So you find the center.
And then like you move like the angle A. So like this line passes through the center, right?
Yeah. Okay, so so let's draw the line through the center now, yeah?
Yeah. And then like you
Yeah.
connect those. I mean this is still equal to angle A.
So this is equal to angle A, right?
Oh, well, now we have like a sec 90
This
degrees.
is 90 degrees, yeah, good.
And like you obviously know sine A is this like this over that. Like
Yeah.
A over the diameter.
So can you see how sine A is equal to A over 2r, right? And then you rearrange it to get that.
Oh.
You see that? And then obviously, if you can show it for any arbitrary angle, you can show it for the 3, right?
Yeah.
So I want to use this as an example of sort of how we're going to go through this, okay? So is this a proof?
Yes.
So this is not quite a proof, okay?
Really?
Yeah.
Sure.
So this is the kind of like because it could be in high school, yeah. If you did this in a classroom, this would be a proof, yeah, and no one would ask a question and it'd be over, yeah. But that's not the level of rigor we're going for, yeah. So one thing that you might think is kind of confused or weird is like, if A was arbitrary, right?
Yeah.
But then it suddenly became acute, right?
Yeah.
Does that make sense?
Oh.
So are all angles acute? You know, because how did an arbitrary angle turn into an acute angle? Right? Isn't that interesting?
I mean, what if it's obtuse and that just makes everything weird?
So you put that small equals also the small triangle. Oh, wait, it's whatever.
Yeah. Yeah, so I really want to use this example, and I saw a video on this actually, and it only covered that part, so it only worked for acute,
Oh, yeah.
and I think that would suffice in the classroom
Yeah.
because no one would ask a question.
Oh, okay, yeah, but in a choose second class.
Yeah,
Wait a second.
Yeah.
Like you know, like sine of like alpha equals the sine of 180 minus alpha.
yeah,
And so you could just change the. I think you can like change the triangle a bit. So
yeah,
The angle, the angle still remain the same, but except like the third one
Yeah.
becomes like 180 minus alpha.
okay.
I mean, that kind of.
So we're thinking. So the reason it's not like necessarily like this, because okay, so assuming that the center's inside the triangle, like on above the base, right, is automatically assuming that's acute, right?
Yeah.
Because those acute triangles have the center inside the triangle, right? So then we can make it go over here, and then it's worked. So we've proven it true for acute acute angles, right? Make sense?
Yeah.
So the main thing is to actually just to be aware of that, yeah. Because once you're aware of it, it's if you keep going step by step, it's more or less routine to get it. So what happens if you have an obtuse angle, right?
You change like the big angle to like I don't know 180 minus. But it's
Yeah. So like you now know that it's gonna have the center outside, right? You guys are all following, right?
Yeah.
No, we really gotta like to make this go smoothly. We really need the people who are not following to be caught up by the people who are following at some point. All these pens not so good. Yeah, we can throw that one away. I think.
wait, cyclic quadrantures.
So if it's obtuse, right, then it's outside the triangle. Yeah.
Can't you get
Yeah. So
the,
you
take
still
the A and you go move up.
you still go through the center now, right?
Yeah.
Okay. So you still get this 90-degree. Well, triangle here, yeah?
But like that small equals like 180
Because
minus
that's-
Yeah, now you get 180 minus a here, right?
Yeah.
But then sine of 180 minus a is still sine a.
Yeah, so you can basically assume this is a for this problem, right?
Yeah.
So, this is still 2r. And this is still a, right?
Yeah.
Yeah. Yeah. So this is actually included in the book. I mean, it's a book written by professional mathematicians, like, and quite a famous one at that too. So I mean, it's included. So it's weird that people would admit it. But yeah, but obviously you don't have the explanation of like that why the other one's not approved, right? So these are the kind of things we want to investigate, yeah. So now it seems like we've proven it for obtuse and acute angles, and there's no other kinds of angles, right? And so since we didn't assume which angle it was, it could have been B or C, right? So then we actually showed that they were all equal. Does that make sense? So that's the kind of like, so when the argument doesn't have any gaps, or hopefully it doesn't have any gaps, it's called rigorous, or it's got rigor. Yeah. And so we're trying to go through this, and the reason a lot of people like going geometry is good is because it's an introduction to proofs, right? Reasoning. So we want to kind of approach it like this. Does that make sense?
Yeah.
That was the extended sine rule. Okay, and so we have an exercise. Okay. Show that for any triangle. Triangle. Like maybe so A, B, C, A, B, C. Like the notation as before, right? A equals B cos A plus C cos B. Let me just check if that's the exercise. So this is part one, yeah? And part two is sine B plus C equals sine B cos C plus cos B So let's see. So 2 is yeah. See, the fact that we're even doing a bit of trig means it's not completely like it's geometry, but it's already got a bit of algebra in it, you know. Oh yeah, and if you so maybe if you wanted the labeling to match the book, this is exercise 1 in the book. It's the first exercise in the book, and this is the second part of that exercise. So this is the first exercise, one whole thing.
Wait, shouldn't there be a B cosine C? In the first one, first exercise.
Really?
This one?
Yeah.
Oh yeah.
Oh yeah, I you said something as well.
Yeah. Yeah. Yeah, so I think this exercise will be good for us to sort of at least define the standard which we want the exercise to be done, right? Because, you know, like, we could definitely just do like 60% of all of them and have them get full marks in school, but not here. All right, if anyone wants to show us their solution, that'd be good too. I don't mind.
Wait, sine 180 sine 180 minus alpha is equal to sine 1. Sine alpha. Sine minus alpha.
Yeah, so yeah, for the theorem, we had to assume that sine 180 minus a was equal to sine a. So that's stuff that I guess we covered before, like the fact that sine is even defined for obtuse angles and stuff. Maybe you can use this as a definition for obtuse angles. Yeah.
Are there still people to this day trying to solve the millennium?
Yes.
Yeah. Well, I mean, there's people who their jobs is to try to solve it.
Oh, because they get paid a lot.
But like then again, chances of you
Oh, a lot of
solving-
people work for grant money, so grants. Like if someone makes progress on that problem, then they get grant money to keep working on it. So
Wait a second, I think I remember this one.
Who made these questions?
the ones that we're doing now,
The millennium.
usually it's like a famous mathematician who like. So one of them is the Riemann hypothesis. then so Riemann made it.
Wait, what's the Riemann hypothesis anyways?
We need to know a bit more about complex numbers.
Complex? Really? I'm pretty sure like 1 over something to the power of n plus 1 over 2 to the power of n plus 1 to the power of c to n plus this equals 0.
I don't even understand this.
Oh yeah, but I think the things could be complex numbers though.
The Riemann.
Why would it be?
Wow.
Why would it be complex numbers?
Because it says like the real part
Zeta.
of the
The
zeros.
real part read an imaginary part of Riemann zeta.
But there's actually an easy version of it that you can understand, I think.
Wikipedia is very helpful to understand.
Huh?
Wikipedia is very helpful to understand.
So there's an easy version of the Riemann hypothesis that's equivalent to it. You can understand
Oh
it.
yeah. Wait.
It's got something to do with like the harmonic function. It's like 1 over 1, 1 over 2 plus 1 over 3 plus.
Okay.
Got it?
Can you see this?
Oh, I cheated.
But yeah, so it's also like
I memorized it for the second question.
but you know, like rigor will also slow you down for the AMCs. It's a good thing you got a prize now. You may not come.
That's gamma function, right? Gamma function. What the hell's gamma function? Me neither.
Zeta, isn't it zeta function? What are you talking about?
I'm pretty sure it's gamma.
The other day I looked up about X factor.
What the heck is this anyway?
And then I found this with
Why do you use decimals? I use this graphic.
Algebra?
No, graphic. It says graphic.
Graphing calculators are like pretty fun to play with, but like you know,
Fun to play with.
but sometimes like they take forever to load. Like it's not even funny. So,
yeah, I got that.
like if it gets graphically pretty like really weird or something, or really screwed up, then like don't even ask.
Weird.
Oh, so do you want to show us your solution? Huh?
You mean for question 2?
Yeah, or 1 or 2.
Question.
Question 2. Oh,
I cheated. I
this is all
memorized
the same question, by the way. Yeah.
Oh, you're trying to prove it.
videos.
Okay, so how do we get part 1? Is it kind of are we on the same page?
Part one's easy.
This is A, yeah.
And then like B, and then B somewhere. I know.
C.
What's the point?
B, yeah.
And you just draw an altitude from A down to
Wait, in
small
that
a.
test, you need it
Yeah.
if you
Length small length x.
Yeah. So what's this length?
X small x like lowercase x.
Yeah. Okay.
This then now my plus be a minus x.
A minus X. Yeah.
So like B
C. Yeah.
which equals B times x over B. No, I mean x. Yeah, B times x over B, which equals to x.
Yeah.
So like this is equal to x. We just
Yep.
And then like C cos B.
Yeah.
Cos B is equal to Bill cos B. Like,
Yeah.
cos B is equal to A over A minus x over C.
Yep.
And times C, that gets you A
Yep.
minus x.
Okay. So then this side is C cos B, right?
Yeah, so like you get this equals x, this equals A minus x. You
Yeah.
get it.
Yeah.
Oh, Bill cos B.
Okay. And so
Yeah.
this length is A. So A is equal to B cos C plus C cos B, right? Okay. So
You need to
Bill cos B.
Yeah,
So this is what I'm trying to emphasize for. So this is why I'm giving you this problem, and I'm sort of going through it. Normally, I'm just giving you the problems for homework, right? So I want to go through this one because I want to kind of so in this question it actually it states it explicitly, but I didn't state it because I wanted to make you aware of it more. I want you to internalize that. Like, so can you see how we've assumed A is acute again, right? Yeah. I mean, sorry, not A. We've assumed B and C. We've assumed B and C are acute,
Yeah.
right? Does that make sense?
Oh, whoops.
And how is it that we've assumed B and C are acute?
because you use that. So that it makes a right angle triangle inside the triangle.
Yeah. So one thing that's special about this triangle is that the height is coming inside the triangle, right?
Yeah, but like if C or B, if one of them is acute, right? That means not acute, like obtuse, right?
Mhm.
That means like
the cosine of that angle is negative.
Yeah.
Yeah, but you draw it out.
So yeah, so this is why we so we're showing for any triangle, right? So this is good, right? Gets you started, and then just being aware of that possibility will get you the rest. So this is still one of the most important steps, right? But for the our standards for homework, it's not enough. Okay. So what we want is first be aware how we've assumed that B and C are acute in this argument, right? And then actually try to deal with the case where one of them is obtuse, right? So I guess it doesn't matter. Well, obviously not both of them can be obtuse, and if one of them is obtuse, you can assume it's B without loss of generality. Yeah. Yeah. So what happens if one of the angles is obtuse, right?
So you draw it out, and then
That's like B. That's C. And that's A. You see the heights now outside the triangle.
Yeah.
But then you can set this one to x, and that one, and then the length of the entire thing. No, the entire thing to be y, because you want to find a. That's it.
So you want this to be Y, yeah?
Yeah. Then y is equal to. I can't draw this sides. I don't know. So
Which side?
the b
Oh,
is
B.
smaller than this. So you want to find a. So x is equal to 180 minus cos 180 minus b times c.
So this is 180 minus B, right?
Yeah. So x is equal to 1 cos 180 minus b times c, which is equal to c cos b minus c cos b.
Yep.
Cos.
So this is because cos 180 minus B is minus B. Yeah.
Yeah. Then you get minus x is equal to cos c cos b.
Yeah. So minus X equals C cos B. Yeah.
And then y is equal to cos c times b. B cos c.
B
Cos c.
cos C. Yeah.
And you add them together, you get y minus x.
So you add them together again, right? That makes sense. And then there's a comment why, so you're not just missing the case that C is obtuse. You're just saying it's unnecessary because you've considered it in this case, with B being arbitrary enough to include C as well, right? That makes sense? Yeah. So so I'm setting you out this so that when I give you the homework problems, you'll know what I'm expecting. Yeah. And if you really have that extra time or brain power, you can even try to explain why the height has to come outside the triangle. Is it obvious that the height's outside when it's obtuse?
If you draw the parallel line and the only point it intersects is outside.
Yeah. Well, if you drew it and it intersect inside, for example, right? And this angle sum is going to be less than 180, but somehow it's going to have to equal 180 because you have angle less than A and angle less than B, and they still add up to 180. There's lots of ways to show it. So you've recognized the second one is the sine addition formula, right?
Yep.
What's the difference between that and the sine addition formula?
You don't have the lowercase lengths and stuff.
Oh no, I mean this one. What's the difference between this formula and just the sine angle? Like, you know how we have sine alpha plus beta equals. Is that the same as this?
Well, it works the same.
Yeah, it's pretty much the same.
Yeah.
The only difference is this is only for angles in a triangle, right? The addition formula works for all angles, all numbers. Yeah. So this is B and C are in a triangle. Yeah.
Oh, yeah.
So otherwise you wouldn't be able to apply part 1 straight away, right?
Yes.
Did you use part 1?
No.
Oh.
Probably wasted some steps there.
Yeah.
Mm.
Yeah. So it's obviously like important to get the answer. So like that's what I'm trying to say. Like, get the answer, and then if you do see connections between the problems, that's also interesting, right? So there's a lot more to it than just solving the problem. There's also the theory building and the sort of the aesthetics.
Wait a second. Oh, that's basic. I think I found new proof to like part 2.
Oh yeah.
But it involves like the, I mean, you know, like the area of the triangle, except like this, you involving sine A and stuff.
Oh yeah.
Nice. Okay.
Yeah, I mean, this is not in the book, but obviously you can also deduce the general addition formula using this addition formula, right? Just have to add some angles. Yeah, it's kind of nice. It almost like the book starts right where we left off. You know what I mean? For geometry.
Are you streaming?
Yeah, about to. Yeah. It's only one person. Right. Well, good. Okay, so let me just write the formulas next to each other. So So it's that, and then we have sine b plus c equals. I guess I'll write it like this. Make it look more like that. So I guess one way to get from there to here, you divide both sides by 2r. Yeah. And so with the sine rule, you know that these are sine A, sine B, and sine C, right? Remember that?
Oh, he seems fair.
Cool, huh? So it's important that, you know, like, these are all for triangles so that the rule applies, right? The R makes sense. Oh yeah, and so sine A is obviously sine B plus C, right? It's 180 minus B. Yeah. Yeah, there's sometimes these sometimes the theory stuff is just a little too elegant. That's why problem solving really gets hands dirty, right? Because like, I don't think it's realistic for this to be the first attempt for most people. And so this is, I guess, you know, there's lots of ways to solve the problem, but this is a nice one in this context because it uses the theory that we had, right? So it relates stuff. Yeah, I guess. At some point, at one point you just care about facts. At some point, you want to care about the explanations of the facts, and then you want to sort of have ways to generate explanations, and then ways to generate those. So it's like the more meta you go, though, I guess the more sophisticated you are. Okay, that was pretty cool, huh? So we're all good? Yeah, and if people don't follow, we have to really catch them up. There's quite a lot of opportunities. Yeah, there's a few downtime. Yeah, this is important. So if you're gonna catch Kavan up, so like for example on Monday, sometimes it's that downtime at the start, you know. So yeah, or like, or even, you know, just like so you have to kind of take responsibility for that. Yeah. Okay, so the next section was Ceva's theorem. So Ceva's theorem. So okay, so there's all these other exercises in that section I'll send you, okay? But the point is I wanted you to sort of know the style of answers I wanted, yeah? Yeah. It's kind of, it was good to be around at that time and prove theorems. Get a theorem named after you forever. I guess you still probably get it named after you, but then like it's probably no one. Well, I guess the ones that become like it's getting a bit specialized now.
Yeah.
And then, yeah. Yeah, this reminds me of this. It's like the charge to mass ratio, like had a unit, and it was called like the Thompson or something because he was doing experiments on that. So I guess if your unit, it's like, you know how charge is like a thing and mass is a thing. Charge divided by mass had a name for a unit. There was a name for that. Anyway, so I guess it depends on how lucky you are too. So basically, the theorem says if you have a triangle, right, and you draw these lines from the vertices. So you can obviously always get them to intersect at one of the sides. And so this one is the interesting one. So you draw it so that they all meet at the same point in the middle. Yeah. So that's called concurrent. Yeah. So I guess there's also the converse of this. So I mentioned the theorem first. So they're concurrent. So if you can draw the lines so that these three lines are concurrent, yeah, then the ratios of these intervals have to multiply to a nice. So this, if this is A, should I use A, B, C? No, this is not good. Maybe I'll use U, V, X, Y, Z, Y, Z, W. U, V, W, X, Y, Z. Okay. Yeah. Then if concurrent, then U on V times W on X times Y on Z equals 1. Yeah. So you kind of just go around like numerator, denominator, numerator, denominator, numerator, denominator. Yeah. And then conversely, if it's equal to 1, right, then it's concurrent. Yeah, so the proof that's given in the book. Yeah, actually, this is let's call these areas W, V, U, Z, Y, and X. Yeah. Yeah. So it uses this trick that we noticed seems to be the key to all these kind of tricky triangle problems, right? It's this when the triangle has the same height, then the areas in relation to the base. Yeah. So basically, the area, so the area like big X to big W is in the same ratio as little x to little w. Does that make sense? Yeah. So basically, I want to show that. U on V is, I want to show U on V is the same as basically this area on this area, or the other way around. Yeah? Does that make sense? Or maybe it's easier to do it from the point of view of X and W, because we're facing that way. So we want W on X, yeah? So W on X, right?
Yeah.
Let's see, is the same as big W on big X, yeah?
Yeah.
Do you agree?
Yeah.
And that's the same as, it's also the same as the height of the big triangle, right?
Yeah.
So it's U plus V plus W. Yeah. Okay. So then, for some reason, okay, that means that these are all actually equal to what I said before was the U plus V and the Y plus Z, right? So it's just U plus V over Y plus Z.
Yeah.
Is that obvious?
Yeah.
So that's kind of interesting. It's not so obvious to me. So it's, I mean, I think it's more geometric. Is it obvious for a geometric reason? It just, yeah. So for me, for some reason, it's easier to explain it if I times this out and cancel out WZ, WX. If I cancel out WX, this is what it took for me to be convinced, because I was not very geometric. So we know these two are equal, right? So if you times them out, you get wx plus wy plus wz, right? Equals xu plus xv plus xw. xu, xv, xw, right? And then xw's cancel. Yeah. So xw's cancel. And then you can uncross multiply again, right? So you get w on x is equal to u plus v on y plus z, yeah?
Oh, yeah.
But you guys could see this kind of more obviously. No?
Right.
It seems geometric. But
Because the areas are in proportion. So if you take off something that's in the same proportion, you're off with the same proportion. Because so, yeah.
Yeah. Yeah. So I guess if you see it straight away, or if you need to investigate further, either way we've verified the truth of it anyway. So, but see, the thing is, if you do this, you'd always feel like you didn't understand something, even though you're more sure that it's true sometimes. Okay, so we're good with that.
Is that the proof?
Almost. So
Oh,
do you get this part of it though?
Yes, but like the proof.
Yeah. So I mean, the proof part is you just put these. So that's w on x, right?
Yeah.
So the point is, you've expressed it in terms of the other two things, right?
Yeah.
And so there's three of them, and so they should all cancel out. So how do you write this? So w on x is equal to u plus v on y plus z, right?
Yeah.
U on v, right? Can you see how it works? It's on so x and w. It's w on x. So u and v is still left to right, yeah. Yeah, so it's the other two. So
it's
here's the one on the
y plus 3 on x plus 3.
yeah. So it's y. So can you see that u on v is equal to y plus z on x plus w?
Yep.
Yeah. And for the same reason, y on z equals, someone else should tell me this because this would help.
Y on z equals to the w plus x on u plus 3.
So that's pretty cool.
W plus x.
Yeah.
Yeah, it's all the sort of, each of these ratios is equal to the ratio of the other two areas. Yeah. W plus x equals, what am I writing here?
U plus v.
U plus v?
Yeah.
Yeah, good. And do you see that what happens now?
Yep, they cancel out in one.
They cancel out, right? Yeah. It's cool. Use clap. Yeah, I guess one big clap or lots of little claps. No, you don't have to clap, it's cool. The guy's dead.
What?
Please, can you just stop? We're like at least 18.
Why?
Cause I don't know.
Who does illegal history?
Why would he do that? Like,
Me and my friends had a live stream at school on YouTube
why would he do
Why'd
that?
you have to suck it?
during classrooms.
Yeah, so
Imagine you secretly live streaming someone from your school for one day.
yeah, so
Imagine you secretly live streaming someone from your school for one day, and then they find out, they're like, holy crap, they're so creepy, stop stalking.
yeah, so I remember when I first tried to prove this. I think I was with you.
Yeah,
we proved it using the sine rule. Yeah. And so I think it actually ends up pretty similar.
Oh yeah.
So like you get the terms and you cancel them out, right? So I've made this realization that the sine rule is kind of really related to this area trick.
Yeah.
Because I mean the whole point is that the sine rule works because of this. Because I mean the whole point is that the sine rule works because of this complement, this 180 thing going on, right? And that happens when there is this area thing going on.
Yeah.
And also, if you just think of the area in terms of the sine formula,
Then it's
then it's related to that's shared, and those angles are the sine, and so it's the half AB sine C thing, right?
Yeah.
And that's proved. You can prove that using you can use that to prove the sine rule as well, right? Because you can just use the area of the triangle in terms of the different corners, and then if you equate them, you'll get the sine rule.
Oh, yeah.
So these are all really intricately related. I think that's the realization we need to come to finish old geometry and revisit new geometry. All right.
Yeah.
To finish old geometry and revisit new geometry. All right.
Yeah.
Revisit new geometry. Okay, so this is something that people can do, is to always hold people accountable for the converse, yeah? Because people always say that there's the converse, and then if no one keeps people accountable, just skip it. I don't know, like, don't do it. But there's something interesting about the converses of stuff, is that like it's somehow related to the other direction, even though logically they're kind of. So okay, so what should I erase? Okay, so what is the converse anyway?
If that,
If that holds true, therefore we can conclude that the C lines are concurrent.
concurrent, what does concurrent mean?
Like if you get C lines and they meet at the same point.
Yeah, so the converse is if. So you just replace the if and the then, yeah. So if it's if we have this is true, right? Then concurrent, right? So I guess in principle, like these could just miss, yeah. Like a priori or whatever. It's like, oh, we're trying so hard. Yeah. I guess if people were walking, but if they're walking at different times, their paths would be concurrent, but they would still miss each other. Anyways. Okay, so I guess what you can do is, without assuming that it's concurrent, you can kind of like join. You can draw one line at least, right?
You
can draw, two lines. They're definitely concurrent, yeah. And so the question is, what happens to the third line, right?
But then summation.
Yeah, so I guess what you can do, let's see, so you can sort of, I mean, maybe you can like imagine that. So we know that the line meets here, right?
Yeah.
But we want it to kind of do this, yeah?
Yeah.
So that's the thing here. Okay, so so it actually meets, so it doesn't meet there, but it actually meets here, right? So let's say this is x prime and this is w prime, yeah?
Yeah, it's good at the
Yeah. So can you see that, like, we know a lot about x prime and w prime
yeah.
because it's actually concurrent, right?
So
So we actually know that x prime,
W prime X prime.
so w prime on x prime is equal to, put all this stuff on the other side, right?
Yeah.
Yeah. Does that make sense? So I shouldn't write it next to the if. The if is here now. This seems to be somewhere after the if, but before the then. Thanks for the like. There's a like.
Like,
Mystery person.
really?
Yeah. I think like most of them we just have as unlisted, but the geometry ones I'm thinking about just making it public because it was such a great initiative that the book.
Thank you for liking. Don't forget to subscribe.
I'll give you the coordinates.
Yeah. It's like I'm just like telling people to subscribe and like, but as I'm saying it, the ads just keep playing, so like it's hard to get to the end of the promo.
Yummy channel.
Yeah, I don't think I have any ads on my channel.
So it's gonna be more than 10 minutes, so by yourselves, you're gonna get ads.
He does have some this one.
No, you need more than like 10K subs or something.
No, you need more than 1K.
1K, yeah. I have like,
And like some watch time, something like 1,000 hours.
Yeah.
when I learn how to upload a photo on my YouTube channel page, that's when we're gonna really make a killing.
Why would you upload your own face on there? You go just
No,
make
you
some
gotta
content
upload on comments.
I don't know. I think once you hit a certain age, like me, when you have kids, it becomes a different interaction with the internet. Okay, so is it clear that so W prime on X prime equals that, right? But we've assumed that this is true, right? So W on X is also equal to that. Does that make sense?
Yeah.
So somehow they're meant to be equal.
Yeah.
Can they be equal and different?
Uh,
So like say if X,
oh,
so if X is smaller, right? If X prime is smaller and W prime is bigger,
Yeah.
then that should be bigger, right?
Yeah.
Because the denominator is smaller and the numerator is bigger.
Yeah.
So that can't work, right? It was on the other side. It was if it was bigger than X and smaller than W, then it should be smaller, right? Yeah.
Did you comment?
Yeah, and don't worry about like if you say anything you want to regret, I could just like edit it.
Did he comment?
No.
Can you comment?
So at this point, this person could still be the people we know, or it could be someone else. We don't know.
maybe Kavan's is really fine.
I don't think does Kavan have enough data to be doing this. Nah, see the thing is, if Kavan was on it, he would definitely say hi, right? He's not a shy person.
Is your name Daniel Sear?
Did you go to Murray Farm Public School?
Oh, I went to Maricon Public School.
Did you?
Yeah, but only for like the last year, like last half of year 6.
Wow, how long have you been here?
I was here in '93.
I remember school's been there since '69, so obviously that makes sense.
Yeah. Yeah, it was way different. I went to North Ryde Public School before that.
My Farm Public School is bad now.
Is it?
Yes. We had a principal that didn't even care about it. But now I think it's good. Again.
Okay. Okay. So are we good with this?
Yeah. Is it good?
So
My future self will look at this on that because I can't write very easily.
yeah, I can send you the notes at some point to look back, and you're like, oh wow, the notes look so much harder than what I remember the actual theorems to be. Okay.
Ask him for his name. What is your name?
He's like, this is too distracting. I'll not stream anymore. Okay.
Aww.
Okay, sure. Let's just concentrate on that stuff.
Then if you're not streaming anymore, what about the other people?
Maybe he's trolling me. Like sometimes he might just log into it and then say, "Who is it?" Like who's on, and it's him.
No, but then I'm watching this, so I can't be watching that.
Is it possible to have data on a different account to your main phone account?
Unless you go Coxeter, then sure, go ahead.
But you
Like say like you're using, I don't know, and then not Vodafone, and I want to share my Vodafone data with you.
you have to like do some plan before you can.
Okay, so I guess I'll just tag it to your phone number or something. Anyway, this is getting. All right, are we good with this?
Yeah.
Do you know like Q-solidity? Can you like is that like sufficient enough?
Yeah, that's the question. Did we miss anything?
Famous issues. Oh yes.
Does it change if it's a 2?
I mean, like if the line some like no, it won't change.
So what did we assume in this argument?
Well, assume that like they
We assume that
intersection
they always
inside.
intersect.
We'll assume they intersect on the inside.
They always
Somehow.
Yeah. So for the converse, we just assumed that it was possible to draw something that intersected. Yeah.
I guess it's like
So yeah, is it always so if you join these two lines, right, and you kept going, do you always end up on this side? Yeah.
no, but doesn't it say that if concurrent if
Oh,
if
if
inside it's inside. If it's inside if they intersect inside then yeah.
Oh, so you're saying these two lines might not intersect inside?
But first like is the W on X equals W prime on X prime like sufficient? That is the question.
Oh yeah, didn't we go through this? So like if it does intersect on this side, right? Say for example, there's two cases, like x prime on the left of x, or it could be on the right of x, yeah? So if x prime's on the left of x, then it's smaller than x, right? And then w prime is bigger than w, right? So then this number is bigger than that number.
Yeah, and then it's the other way.
And if it's the other way, then it's smaller than that number, yeah?
What happens if u is equal to 0?
0.
No, but then that means it would just be a sign.
Yeah, I guess we're not allowed to have it be a side.
Yeah, it seems so.
Yeah.
I mean, it might, but then no, it's
Yeah, I mean, if you express this without denominators, and just have them equal,
because
would one of them have to be 0?
yeah, or 0.
Does u, v, or w, does u, w, or y have to be 0?
Or maybe if like the lengths are somehow negative or something, I don't know.
Yeah.
I mean, that kind of works too.
Okay, well, yeah, so I guess those are the degenerate cases that probably actually fail. Yeah, and I guess, yeah, like, and it's sort of your job to keep me accountable for wrong proofs, yeah? Because that's the whole point of having, I guess, an audience. I think traditionally it's like someone's meant to see something wrong if it's wrong, you know, and then point it out or like argue. That's why like the inverted classroom thing, it takes that away. Like it makes it like you're assuming it's right. And I think you should always approach things with a little bit of, you know, I don't want to call it skepticism, but that's skepticism. So that's the first two sections, and I want to point out one of the exercises. I think the exercise was like this. So the very first exercise in that next section was basically if you had a triangle and you draw it to the midpoints, right?
Oh, median. Okay.
I guess that's called a median, yeah?
Yeah, but like what's... Oh, is it inside out?
And then show that it's concurrent. Sorry, that's meant to be a straight
That
line.
was very rushed. Very short. Go ahead.
It's funny because I took too long going across. That's why.
You just use save this here. Okay, nice.
Yeah, so this is what I wanted to point out. So I guess it may depend on how much time you have as well, right? So it says if x, y, and z are the midpoints of the sides, then they are concurrent. Yeah, that's basically what the question was. So if x, y, and z are the midpoints.
It's application of.
Yeah, so I guess you should at least notice that this is a special case of the theorem, right? Because when they're all the same, they all cancel. Yeah, it's like because this cancels with this right away, right? With 1 times 1, yeah, okay. And you know, you could just say that as the homework answer, okay? And it's definitely a valid point, and it's important, right? But I guess you might also want to see if you could prove it. Okay, so another approach maybe to go through the proof of Ceva's theorem and just assume that they're midpoints to see if anything simplifies, yeah? Or even better, maybe you can come up with something more like, you know what I mean? Like, So Ceva's theorem obviously works for all possible ratios of these sides that add times to 1, right? But there might be something special about the midpoints that you can take advantage of to make the argument even more efficient or more elegant. Yeah. But this is for homework, okay?
Wait a second.
So it's
Yeah. Yeah, the areas are actually all equal, aren't they?
If you just
Right.
What are we showing? Oh, they're concurrent. Oh, no, so the area. So this is not defined. Yeah. So this is like you could be going like over here. Yeah.
Oh, okay, it makes it more easier. It makes it like the proof like so easy, like for the ending.
Yeah.
Yeah.
So like I'm okay with anything you hand in, as long as, well, first of all, it solves the problem. Okay. But I'm just making you aware there's obviously different degrees of, but like sometimes you're just not interested in the question. I can understand that too. But the earlier ones that you're learning, it's kind of should be interested in most of them. I think just being unfamiliar with stuff is interesting.
It makes it hard.
Yeah. But if you've seen it before, or if it's tedious, or you've kind of gone through it but can't remember, I don't know. I can understand.
Yeah.
Whose copy is this? Wait, yours. Do you bring a copy? No, then spoilers. Do you bring a copy? No, then spoilers. It is. But did you bring a copy? And yes, I did. I thought I did.
What? Yeah, that's definitely.
I don't know. I left it up. Oh. I can get the juice from the juice.
You want more juice?
Well, juice.
This doesn't work.
Oh, did we?
There's another one.
There's another one. That's a pear juice.
I don't know.
It's really good. I do really good. There's similar triangles. SAS. Wait, how much noise?
This does work good.
I only just realized if you use similar triangles. That's it. That's also good. See this.
It's apple pen.
Is it-
It's apple pen.
Is it good?
Oh, I guess. It's like
That's the kind of YouTube live stream. What? It's like a live stream.
Leah went on just now.
Are you sure?
This looks so fun. It's that. I guess.
What? Like you can't even see the thing because like
Because they write it out and they make it seem nice and everything.
yep, my hand covered the thing.
Oh no. Click. Oh yeah, you can see.
Why would you? Okay, you just made your first face review online.
Nah, lots of people.
Well, why is it? It doesn't want first looking.
I presented on that on live stream.
It's like legitimately only one person. And like not even that, not even that. It's mainly like live for like 90 minutes. And like not even that, not even that. It's mainly like live for like 90 minutes.
Streams just to save it, like save the video, like ingrain it in history.
He goes just like film like Eddie Wu. He goes just film like Eddie Wu.
Yeah, what?
Eddie Wu.
Yeah, he's famous.
Like he's like the most famous math teacher in Australia or something. So like his videos are entertaining to like, and there's also like
Gives me an unrealistic expectation for math teachers.
exactly. So we should all be like Eddie Wu.
All right. Yeah, so that's all we're gonna do for geometry. And so
now
there's two homeworks that I'll send you. Basically those sections, yeah. And I kind of want to see how we go through it, because obviously how fast we go through it and whatever is up to you. But also, it's never really that quick going through a book. I'll give you a little bit of a preview of the algebra we'll do.
oh, algebra. We'll start the section down here.
Yeah, do you want another book?
Do we need another book?
Is it gonna be that many?
So the geometry one's going to take a lot of space. Algebra, I don't really know how. This is really depending on you.
It's not my math.
Yeah, we go just right on the back, right?
Okay.
No, I was gonna start my homework from
Oh, okay. You can have another one.
there. Yeah, because I need a PE book for my something.
We can't be like, let's, at the start.
let
we
us
need
all
to be
take
generous.
It's all taken on. I'm very sorry. I'm incredibly sorry.
This is also good. Except
David, you wouldn't believe that this is not the first time that that's happened.
because you always do.
I'm on.
Whose juice was that?
Mine.
I'm incredibly sorry. I shouldn't have done that.
Damn it, this is my stuff. How is this my stuff?
I'm gonna ask you when you get me seconds.
Did you see?
Oh, well, I did get wet. Never mind. Just let it dry off somewhere.
Yeah.
I'm very sorry.
No, it's fine. This one is all good.
Well, at least there's a life lesson.
It's fine.
When I say fine, I mean it's a fine of.
Yeah.
I'm very sorry.
No, it's fine.
This one is all good.
Well, at least there's a life lesson.
It's fine.
When I say fine, I mean it's a fine of like.
Well,
No, I'm just kidding.
Often 600 all fine.
I guess it's good.
Oh, the orphan paper.
on the head.
They never treat orphans well, do they?
I have no idea other than 5.
Alright, then you just have to throw it
it
out.
smells
Yeah.
quite nice. Not gonna lie.
You need to cut this in half and use half of the offer.
Have you noticed like all these colloquialisms are just like they imply people are like intrinsically dishonest? It's like this. What the hell? Not gonna lie. To be honest, you know, it's just like everyone's like, well, what do you normally? Just like always,
Always lie.
just like always
When
like
I'm not
understanding
saying,
stuff.
when I'm not saying not gonna lie, I always
Yeah,
lie.
Not gonna lie. To be honest, and so what do you do normally?
I lie. I do not be honest.
It's like
To be honest, generally, when you're not the next thing you're gonna say.
Be
honest,
I tell you what
you think.
it's like it's like when you really want to deceive someone, you tell them you're being honest.
Get that one. So, in case it's so.
Yeah,
Yeah, that's yours.
Yes.
Yes.
No.
It's non-effective paper.
Yeah, just put
Oh, no, you break
it
it.
on. Put it on. Okay, we've done this.
We just shove it in, yeah.
Oh, you use that paper stuff in there.
Ah,
Yeah, all that is trash. See, I made it extra big so you wouldn't miss,
I thought it's so.
but there's still some that are missed.
Oh, yeah. Put that.
I have you in.
No, guys, it's really. I think I need another table. That's what I need.
This table like kind of cheap.
Yeah, I'm gonna. Should get another one. Yeah.
A bit of
I
I
don't
get
know
more
what to get in
chairs
live
too.
stream.
This is a barbecue table.
Yeah, but like there's also rubbish.
These are like the
My stop
best.
paper.
When it says lifetime table, like I believe it.
Those are my stop paper, which I do not want to see my life in the trash.
Alright.
The big eats. Bye bye. Anyways, wait, is that stop paper?
That's.
Screw it. Yeah, screw it. That's not.
Algebra.
I'm watching Zombie 7 this
I'm guessing that.
We confused what happens.
Is he still watching?
War break out.
Yeah.
I didn't know about watching. I just listened to the stuff.
Well, hopefully, like, see, the thing is, if you have, there's like at least one problem that hasn't been solved on the board. Hopefully people will use the downtime efficiently, because there's always something to do, right?
I already have 3.
That median problem was
Really?
up there, for example,
Oh,
right?
wow.
Thank you.
Why can't
Yes.
That's the thing. Like, you're catching a bus, you're catching a train. There's always something you can do in that time.
I wasn't
Whereas
thinking.
it seems like Kavan just plays games in that time.
I need another one.
It's
Are
hard
you
to-
serious?
Yeah.
I do not believe you.
Standing.
It's like as
Oh,
if
yeah,
you
it is.
expect it to stand. It's not
Yeah,
so
you lied to me.
Really?
Yeah.
Yeah, I guess it depends where you go.
bad. School. Yeah, because you need to be polite. Give up your seat when there's someone there.
It's true. You gotta stand and think. You gotta do it in your head.
Yeah. Yeah, no, above your head.
Yeah.
Algebra. How it goes.
All right. So I'm really interested in groups. Groups are very interesting to me. So what are groups? Yeah. Groups. Okay. So basically, we're kind of studying these axioms. Yeah. So. Okay. So maybe we have a set. Yeah. And an operation. Yeah. So maybe we'll call it the operation at dot. So we have a set G and an operation dot. Yeah?
Yeah.
And so the operation is associative. Yeah, so that's the first thing. So let's see. X dot Y. Oh, I did this backwards. I'll write it properly. X Y dot Z. Yeah? I don't really need brackets on the outside. Is equal to X dot Y dot Z for all X, Y, Z in G. Yeah? Yeah. Yeah. So this is basically saying, like, it doesn't matter how you bracket the elements in pairs.
So what is G again?
Oh, it's a set.
What does X dot Y mean, anyways?
So like, imagine if this is a plus or a times. You know, imagine if this is a plus or a times. You know,
Yeah.
it's like X times Y times Z.
Yes,
Yeah.
exactly.
Yeah, but we just didn't write times symbol because
It's just some operator.
yeah, so any
Same
operation.
size that.
Okay, so 2, there it is. Let's call it U in G such that U times X equals X times U equals X for all X in G. Yeah, that makes sense. So there is one element in G, right?
Yeah.
That when you times it with other stuff, it doesn't change the other stuff. So for example, it was multiplication, you have like a 1, you times it to stuff, it doesn't change stuff, right?
Identity.
Yeah, called the identity. Yeah. So this is called associativity. This is called identity. Existence of identity.
Sure, you put I instead of something.
Hmm?
Like with I, see nice.
Yeah. Or E, I think E is used actually a lot. Yeah.
I thought it was like I in matrix.
Oh, capital I, yeah.
Yeah. I did. Yeah.
Matrices don't. Well, anyway, so 3. What's the last one, you know? So this is for every. No. So for every x in G, right?
Yeah, there exists.
There exists a y, x dot y equals.
Okay.
Well, that happened again.
Bloody hell.
Well, that's like his fault. It's like,
That's
his fault. It's not.
Sorry.
Lift the book up. Save what you can.
Guys, tissue.
No, it's gonna go everywhere.
I don't even know if I can tell
What's on
these.
your book? It's on your book.
You know these. Did you spell it?
It's not on my books.
I don't even know if I can tell Lisa about this.
Don't worry, we'll
This
come
is
to
too
it shortly.
shameful.
We do so many stupid things. Okay, there's barely anything on there based on this thing.
It's like accelerated in maths, but handicapped in drink containing.
Just like all this. Imagine if you actually were on the whole thing after you read this answer.
Oh, it's so sticky. Why is juice so sticky?
It's made from fruits.
Like,
And sugar is sticky as hell.
I'm coming for ants to discover you.
Jeez, is there any baby wipes or something here?
Baby wipes.
Or wet wipes or whatever the hell they call them.
I feel like my position gets attacked in this or something. Oh yeah, his fault. He's actually attacking you.
It's not assassination.
I'll try not to spill this.
Let's just get this out. You should drink it.
I'm gonna get another table, guys.
I think there's some. Yeah,
And I'm gonna get like a bucket that you can just pour water into.
I think it's probably.
No, you should get two tables. One table for the drinks and one.
Why would he
table
do
for
that?
things.
That's like the dumbest thing. That's like the dumbest idea ever. Don't do that.
It's like when you like.
I'm gonna put it in the most precarious position I can.
It's like when you don't make adjustments. Like it's like.
Nothing happens. Nothing happens. You know, just chilling.
See, the thing is, if they were my books, I'd have to like buy new books and then give them to you.
Oh my
But
God,
since they're
that's
your books,
Why would you put it there? Just like put someone
Now.
I'll actually have to do that for the same.
all right, we still have another 40 minutes.
I'll
40 Minuten. Yeah. I mean, there's only so much drink that can be spilled, and that's 4 liters.
Oh no, that's milk.
Oh, that's infinite. Yeah. Can we close the door so that no one else knows about this? This drink spilling, I must admit, is still better than the wall marking. Okay. I don't know where those black marks are, but it's like.
To be honest, I don't understand any of this. I'm very sorry.
Oh no, it's okay not to
Yeah, I don't
understand
understand any
this.
of
This is not understandable yet.
Yeah.
You finished it?
Oh no! So last.
Oh, what?
Oh my god!
What are you doing? This is how that happened.
It's like every
I
action
thought there's
you
like
do.
juice over that.
Every action you do has a risk of spilling juice.
The action reaction.
So it just makes it a matter of time.
Oops.
All right. Okay. So for every x in G, there exists another y in G. Okay. Such that x times y equals y times x equals that identity u. Yeah. So this is the identity.
What?
So this is already a problematic statement.
Also,
What's
there's,
identity?
I don't get this. Wait, so you have x times
so
one.
like real numbers and so like
I need multiply groups.
so you have for addition you have negatives for multiplication you have the reciprocals and then for multiplication x would be 1.
Yeah. So if you think
No,
about
x u would be 1.
so can you give me some examples of groups then? Yeah. So you're telling me about multiplication, right?
Yeah, what is group?
multiplication and all.
So what's the
real
set? What's the set?
numbers. Real numbers.
So real numbers,
Not real
and then what's the operation?
You include spirits. Yeah, that's weird.
So-
rational. Yeah, rational numbers. Yeah.
So we're talking real numbers or rational numbers?
you don't need to include.
I didn't say
Okay.
real. I was like,
I think real is fine. Okay.
The rational.
Oh yeah.
So what are we doing? So real numbers, what operation?
Multiplication.
Multiplication. Yeah. So is that a group?
Yeah.
Yeah, we satisfy all those.
It's almost a group.
Right. One. Yeah, zero.
So zero. So what? So yeah. So to make it a group, okay, you got to find a one, right? So that's a one, right?
But
It's all associative, yeah.
Yeah.
But is every element have an inverse?
zero does it.
Zero doesn't, right?
Oh, and 0 multiplied by by 1 doesn't give you. Oh,
It does,
Yeah,
it does.
yeah, sorry. Never mind. It's still giving you 0, yeah.
And also infinity, which isn't a number, but it's not
Yeah.
reciprocal.
So one way to solve that, you just let the set have no zero in it, yeah?
Yeah.
So I guess one way to say that in set notation is you take this zero out, yeah? And then you say multiplication, and that's a group, yeah?
Okay.
I really hope you can explain this to Kavan.
I didn't get this question. Could you explain?
Huh?
Yeah, this seems weird.
Yeah.
So we're basically studying things with these three properties, yeah? We're just going to study the properties.
So
Yeah.
what's the first one?
Yeah.
The first property is that it's associative.
So x multiplied by y is equal.
So the point is, if you have an operation that takes in two things, right?
Yeah.
Like multiplication takes two numbers and gives out one number, yeah?
Yeah.
Like, what do you do when you have three numbers? You can't put three numbers in at once, right? You have to put two numbers in first to get a number out, and then pair the answer with the last number, right? But you could pair them in different ways first, right? And so this is just saying it doesn't matter how you pair them. Oh, well, actually, literally, it's saying it doesn't. If you pair the second two, it's the same as pairing the first two. Okay, but as a consequence of this, it doesn't. Oh yeah. The
Who's Nathan?
It's a small little
Come on.
it's like it does not uniquely define.
The one that was primary school one, yeah.
Yeah. No, he just has the attention span, doesn't go long enough, but he's very good. So anyway, yeah, so there's some exercise with this. You can obviously show that see, because you pair the second and then do it with the first thing, right? And we pair the first and do it with the third thing, yeah? But you could also pair the first and third and do it with the second thing, right? But that's a consequence of this, actually. So
Now, what is number two?
okay, number two means there exists something which doesn't change other stuff when you use the operation. Okay.
Oh, for basically like u equals 1.
Yeah, like in this case it's one, right? Because one time stuff keeps them the same as what they were. So if the example was this set, right?
Yeah.
U would be one. Because
Something-
one times anything is the same as that thing. One times x is x, yeah? So that's what u does, right? And I wrote it like this because it's not, we haven't assumed that u times x is the same as x times u in general, yeah?
Unless if x equals 0, then u can be anything. So,
0 is not exactly. We're going to define them 0.
Yeah.
or nothing, or whatever.
Okay.
So addition and the identity u is 0.
Yeah, so if you want to do addition, what set do you want to use?
Just real numbers.
Real numbers, yeah. Okay, real numbers.
Equals 0.
Yeah, include everything, and then you do addition, right?
Yeah.
So can you see that works?
Oh, it does.
U that's u be 0 and
So when we say this, we mean that the dot is equal to the plus, right?
The operation is.
you might want to just write identities in case they get
Yeah, so we might also want to write the identity. Okay, fine. So yeah, but see, we haven't shown it's unique yet. So we guess we just need one to witness this property. Yeah. So here it'd be 0. Yeah. And here it'd be 1. Yeah.
That seems.
Yeah, because everything has a negative. Yeah. Everything. There's absolutely everything. Yeah.
What about exponent? Like, say, like,
Does it work for
You just-
exponents? Let's try it.
I'm like, u to the power of x is not necessarily equal to x to the power of u.
Oh yeah, but we don't have that. Oh, exponents. You mean you want to make the operation exponentiation?
Yeah, but like, only work for some cases, like 2
No,
and 4.
no, so it's not really. U would be 0.
You
0 to the power of x is equal to x to the power of.
Oh, but for the first
Really?
one,
Okay, fine. Does it equal to x?
first one doesn't.
Yeah, first one is 1.
well, I mean, you can sort of change multiplication into addition by using exponents.
Oh, yeah.
So there's some things you can do, but yeah, like,
Just by those or that.
What else is it? What else does it?
Oh, you mean what's not a group?
Yeah, what's not good?
Subtraction not a group.
Yeah, because like u minus x is not necessarily equal to x minus u.
Oh, subtraction.
Unless that gives you 0 or whatever. Then sure,
Yeah.
go ahead.
And then
Oh, you got 0 minus 6.
division doesn't work.
Division doesn't work.
Unless
Oh.
if u equals x, and that gives you something like either 1. In this case, go ahead.
Experiments.
Wait, why doesn't subtraction work? Could you say it explicitly?
Because then the units have to be 0. You like because you get x minus u has to be x, so u has to be 0.
It's not associated.
And also that breaks this rule, because like x minus 1 y plus z is not equal to x minus y minus z,
Mm-hmm.
So
which actually seems fair if you think about it.
Yeah. So
because
y
the
minus.
last on the bracket is the last on the bracket is
Oh, so like you're saying like x minus y minus z, right?
It's not equal to. It's not equal to you unless it's equal to
X
0.
minus y and then
Plus
minus z.
That's like the other version.
You know,
yeah.
only works if z equals 0.
So they're not equal, yeah?
If z equals 0, then sure.
Yeah,
go
so
ahead.
subtraction
Go
fails a lot of ways.
Yeah.
But subtraction is really just addition of negatives, yeah?
You can't
So it's like two operations at once. You take negatives and then you take addition. So it's not too big of a problem. Yeah, and obviously, so you can have real numbers, you can have rational numbers, you can have integers. Yeah. So I guess part of I didn't really say it explicitly, but the operation is meant to take two values from here and back into there.
Yeah.
So it would work for integers, rational numbers, all this stuff you're kind of familiar with, right?
Would it work with complex?
Yeah, but what operation?
Complex numbers, yeah. So it would also work. So it's the same thing basically. If it's multiplication, you're gonna take out 0, and it would work with 1. Yeah. If it was addition, it'd be like this. So it would work with complex numbers. Okay. And then this is not a condition for groups, but commutativity. You know what commutativity is, right? So this is when like you can swap the order of the operations. So x times y is equal to y times x for all x and y. So if it's commutative, then it's called an abelian group. Yeah, it's named after someone.
Obviously, it's named after someone.
Yeah. Yeah.
So,
And then there's some other kind of rules like distributivity,
Yeah,
but you need 2 operations for that. Yeah. Okay.
So what are the types of groups?
Yeah. So there's lots of finite groups, and that's the one we're going to be interested in. Okay. So. I don't know if I should take some time to put groups in the perspective of like all those algebra things. So like this is just one operation with these nice properties, right? Yeah. Called a group. If you had 2 operations and there was distributivity, right? That would be like a field. Yeah. And if you had 2 operations and you had distributivity, but there wasn't an inverse for the multiplication, then that'd be called a ring. Yeah. So there's all sorts of like ways you can break down these things, you know what I mean? But like this is obviously fundamental because this is sort of a part of all of those things. Yeah. Okay, so maybe we can just come up with more examples now. So should I keep the conditions up there? So the integers are interesting. One of the things that we did, remember the integers modulo p. Remember this?
Yeah.
The remainders when you divide by a prime. So that's a group. Do you know what I'm talking about? So like 0, 1, 2, 3, 4, up to p. Well,
P minus 1.
yeah, I guess up to p minus 1, because 0 is the same as p, right?
Yeah.
And so can you see how that's a group?
Oh yeah, it seems that.
Wait, multiplication. Wait, what's something?
Yeah, that's what we're trying to figure out, I guess. So, I mean, there's only two natural operations to think about at the moment. Yeah.
Yeah, both multiplication and addition.
Yeah.
Addition is definitely true. Multiplication, yeah, it's all true.
Yeah, so actually, to sort of make it very clear, so as it is, addition makes it a group under addition.
Yeah.
Yeah. Makes sense? To make it a group under multiple, so addition modulo p, yeah?
Yeah.
You know what I'm talking about? Yep. Okay. Multiplication modulo p, provided you take out the 0,
Okay.
right? Because you can't invert the 0.
Yeah.
Is it obvious you can invert the other stuff? It's not so obvious, is it?
Yeah.
So, I mean, the point is, if you have like 3 and 7, right? You have to invert it mod p, you know what I mean? So, sorry, if you have 3, you want to invert it mod p, yeah?
Yeah.
So you need to be able to times it by some x, yeah? So that's equal to some multiple of p, right?
Yeah.
Plus 1, yeah?
Yeah.
Does that make sense? Yeah. So that's what inverting at mod p is, yeah?
Yeah.
Well, can you see that's just the solution to that weird equation we had? 3x minus kp equals 1. And so k, so the point is p, sorry, this is, yeah, this is a p, right?
Yeah.
So the point is p and 3 are co-prime.
Yeah. Oh. Okay.
So then there's always a solution for k and x.
Yeah.
Yeah? So therefore, this is a group when you take out 0 for multiplication. It's a group when you add addition, right? And if you remember we had the language before, if you combine them, it makes it a field. Because it actually distributes over addition as well, right? So that's the nice thing about primes as well.
Like, do you distribute in one piece?
Yeah.
Like, in one piece?
Yeah, so distributivity is like this. B plus C
Yeah.
AB.
Does it work in
Oh yeah, distributivity works in mod P, yeah. I mean the operations.
Yeah, it's true.
So because you think about how you're taking mod P, right? You do it A and then B plus C,
Yeah.
and then B plus C is B and plus C, yeah.
Is that an inverse for distributivity?
Inverse.
Like, so, for distributivity?
Inverse.
Like, so, backwards or...
No. So it's not symmetric. Yeah, I made this mistake at some point. It's a long time ago.
Yeah.
But it definitely has to be addition, and then the multiplication has to distribute over addition.
Yeah, like, if you, so like, if AB plus AC equals A.
Yeah, so what happens? What would distribute it? So it'd be like this, right? Is this, you're saying like if you reverse the roles of the operations?
No, like, if you, like, so before we had A times B plus C is equal to, AB plus AC.
Yeah.
Is there exist stuff that's like AB plus AC does not go back into that?
A, B plus AC.
So,
Oh, it does not equal that.
yeah,
Oh.
like, so, because you can have stuff that's not distributive, right? So,
Mm-hmm.
can you have stuff that's like going backwards, sometimes some stuff that's not going backwards?
N equals 0?
So, like, not factorizable or like they can't factorize.
I don't think so. Not if you have like the operations in the same place. You know? Wait, I'm still not quite understanding.
Like,
yeah.
so we have distributivity as a property. Do you have to like reverse of distributivity?
Is there some way that you can do it? You can distribute it by maybe with that.
Oh.
So like A like A dot B plus A dot C does that always have to be like is there a property set for like A dot B plus A dot C is equal to A dot B plus C? Is that a property or?
Wait, so you say that again? So A dot B.
It doesn't have to be plus, right? We can just dot B plus A dot C
Yeah.
is equal to A dot like B plus C or B plus C.
It's not equal to. Wait.
Like, so, because we have A times B plus C is equal to A B plus AC, that's distributivity.
Yeah.
And then if we have that going backwards, is there a special property name for that property? Or because like.
Oh, I guess distributivity should be both ways. Yeah.
Okay, yeah.
Okay. Yeah, it's not just a left to right thing.
Yeah.
I guess distributivity should be both ways. Yeah.
Okay, yeah.
Okay. Yeah, it's not just a left to right thing.
Yeah.
Yeah. Interesting question. Yeah, I guess it's sort of saying the second operation is compatible with the first operation. So you're kind of building on top of the first operation.
So like exponential is a distribution.
Exponentiation. Oh, you're saying if you take two other, like if you take this as multiplication, and this is exponentiation.
Yeah, doesn't it work? Yeah, that's okay.
Let's have a look.
It's equal to A power P times A times
Times A to the power C.
A to the power P C is equal to
These would add, wouldn't they?
Oh wait. No, that's
Huh?
Wait.
Oh yeah, they do add, yeah.
Yeah, so this is interesting, and especially interesting because it's an example of a finite.
Yeah.
So there are some more things we need to learn about sets to really learn about all these things. But yeah, does it make sense if I say what like a permutation is? So let me just. I can erase this. You remember these 3 points now, right? Yeah, I guess we should also come up with some trivial groups as well. Like if you just had like a set of 0 or 1, I guess.
Yeah.
That's probably more. It's nicer.
Yeah.
0 is hard. That's a group. You could have plus or minus. You can have 1 and minus 1, right? That's a group.
Yeah.
That's actually this with 2, right? P equals 2.
Yeah.
Well, so we can say it's isomorphic to that because you can correspond the elements.
Wait.
So that the
Is
most.
a minus 1 just 1?
Oh, sorry. I'm talking about something wrong.
Okay, mod 3.
Wait, what am I doing? It's
Maybe
multiplication.
Mod 3 then, I guess.
Yeah, it's
Well,
multiplication and it's Z mod 3.
Yeah, and then you need the 0 now. So.
And then take out the 0 if it's multiplication. Yeah. If I have addition, I need to put in the 0. And then it'll be Z3. Yeah. Excellent.
Well, haha. How was this up?
That's
Oh wait, well, hang on. Now for the for two things that multiply to become the identity, then the identity is going to be -1.
Which one? This group?
Yeah.
So what's the identity here?
Okay, well,
So we're doing multiplication, yeah? So the identity is 1, isn't it?
Yeah, it has to be 1. But then if you have the thing like,
Because it's its own inverse, yeah?
Yeah.
That times itself is 1, that times itself is 1. So each has an inverse. This one doesn't change anything when you multiply. And what's the other property? It's associative, yeah. think of some more examples. So this is like a pretty key example. So the permutation group, yeah?
Yeah.
So this is the, as a set, it's the set of permutations of n things, yeah? Make sense? Maybe one way to represent it, maybe we just consider a small case, yeah, like S3, yeah? Maybe to represent a permutation, we can just have like 1, 2, 3, right? And we can see how to scramble them up somehow, right? So the obvious permutation is that something that doesn't do anything, yeah?
Yep.
So we could swap the first two things.
So the last two things.
Oh, you're not including the small ones.
Oh yeah.
Do you include the small ones? Like the two numbers?
Oh no, just n.
Okay.
1, 2, 3. 1, 2, 3. You could cross out the 1 and 3, right?
Yeah.
And try to draw them so there's no like concurrent lines. 1, 2, 3, 1, 2, 3. So they're the ones we can swap to, right?
Yeah, now we swap.
You can cycle them as well, yeah. So you can move 1 to 2, 2 to
3.
3, and 3 to 1, yeah.
4, 1 to 3.
2 to 1, 3 to 2, yeah. That makes sense? I think that's all of them.
Yeah.
Alright, so that's the set. This is it obvious that there should be 3 factorial things in here?
Yeah.
Yeah. And do you know what the operation is?
3, 2.
Or what a kid could be?
Mm.
Like how do I get from so what's the identity by the way? Well what would be the identity? Like you don't know the operation, but like what would be what do you think should be the identity and then
1, 2, 3.
huh?
Okay, let's go.
This one, yeah?
Yeah.
The one that does nothing.
Yeah.
Yeah. So you can think of the operation as just like because what that is, you're doing something to 1, 2, 3, right?
Yeah.
So you can think of the operation as just doing it again, like doing it in like composing the doings, composing the
Yeah.
actions.
Oh, is this operation? Wait, no, that wouldn't be operation.
So one way to express that is you could actually like, for example, if you wanted this dot this, right?
Yeah.
You could actually just put them next to each other and
Oh yeah.
follow the arrow all the way to the end.
Yeah.
Yeah. So for example, this dot this could equal 1, 2, 3, 1, 2, 3. See how like it goes 1 to 3, yeah?
Yeah.
So we say 1 goes to 3, 1 goes to 2 goes to 2, goes to 2, and then 3 goes to 1, right? So it happens to be the same as the second thing.
Yeah.
And if you think about it, doing nothing and then doing something will always be just the same as doing that
And
something.
the inverse is just the one that takes back.
Yeah, it's just doing the opposite thing, right? And because we've done all the possible combinations, there must also be an inverse.
Yeah.
Because we haven't sent anything to this, like we haven't lost any. And
Wait, doesn't that mean you can like something dot equals you don't need 2 things, do you?
something,
Wait, no.
say again.
Wouldn't that mean you can just use one thing and stop that? Never mind.
Yeah, but kind of, if you just imagine you're working with 1, 2, and 3, right? And you're doing something to them. You're scrambling them up, right? And the operation is just to do the actions in sequence. Yeah.
Like it's
Yeah. Sure.
oh,
Yeah. So the thing that doesn't change it is to do nothing, right? Because if you do something, then do nothing, then it'll be just the first action, right?
How to choose things.
Huh?
Like, isn't that already an operation? Like it's that. So
What's an operation?
the scrambling up of
Just
that's
putting them
operation on
together?
one thing,
Yeah.
They put an operation on a single thing.
Oh no, we're thinking of the operations on these 6 diagrams. So, because this is the set. This is the set of 6 things, right? We want to think of how to pair up each of those 6. Pair up pairs out of those 6 things. So we want to get any 2 diagrams and produce another diagram that's on the list. That's another one of the 6. Yeah.
Well, since these are all possible combinations, and everything is good.
Yeah. Right. So for example, if you want to do 1 goes to 2, 2 goes to 1, and 3 goes to 3, right? To undo that, you just have to do it again, because all this did was did nothing to 3, right? And swapped 1 and 2. So if you do that twice, it's going to unswap 1 and 2, and then keep 3 on nothing. Yeah. So this is a group, okay? And this is going to be a key example of a finite group, right? And then I think it'll be like a success if you understand why this is the key example of a finite group. By the end of it, yeah. Yeah, I guess. So maybe I want to explain. I can also express this in functions, right? You know, so I guess I have to explain more about a function. But these are exactly all the bijections of 1, 2, 3, right? So they're the functions that, yeah, the functions that don't like send 2 things to 1. Like they basically has a 1-to-1 correspondence, and it's like every yeah, everything goes to exactly one thing, and everything's gotten, you can go backwards. So basically, they're all the functions that can go backwards. They're all the invertible functions on 1, 2, 3. And some more examples of groups we've encountered. Yeah. Usually, so one of the insights is that they come from symmetries. You can have symmetry groups, like, for example, you could have all the sort of like rotations about some fixed point, right? And you can think of 2 rotations as operated as to do 1 rotation followed by the other one. And so then the identity would be doing nothing, not rotating. Doing the inverse would be just unrotating it.
Like going the other way.
Yeah. Okay.
Is he still watching?
Probably. Yeah. So okay, maybe I need to give you a problem to solve.
Hey, dude, tell us your name.
No, stop being annoying. So prove. So I guess we were kind of a little bit of trouble with saying the identity because we didn't say it was unique, right? Can you prove the identity is unique? Yeah? So for every element, so there can only be 1 identity. It can't be 2. Does that make sense? So there's just 1. There's no other 1, right? There's no other 0. Prove inverses are unique.
Let's see. Prove identity is unique. It's 1
Huh?
1, I think.
Okay.
Do you assume that there's 2?
Okay, so what do you call them?
U and U.
The U and U prime.
Yeah, fine.
Okay, so assume U and U prime are identities.
Then U times U prime. U operation U prime.
So U dot U prime, yeah.
Should give you U.
Give you. So yeah, I guess you're assuming.
Wait. They're both identity, so u times x will give you x, right? Then it should be u prime, not u.
Okay, u prime. So you're using the identity property of u, right?
Then you use the associativity and you switch it around, and you get u prime dot u.
And because it's identity, then u dot u prime is equal to u prime dot u.
Yeah.
Yeah. So u prime dot u
Yeah.
is equal to u dot u prime. Yeah.
Equals to u. Yeah. Equals to
So
u.
that's either one of the whichever one you assume to be identity would give you that, right?
And then since u prime dot u equals u.
Yeah. So this is equal to u by the identity property of u prime,
So it's
right?
equal to u prime.
Yeah.
So it's,
Yeah. So therefore they're equal, right?
Yeah.
Does that make sense? Yeah. Cool. All right. Two inverses are unique. So let x and g, I guess. I want to say like y and y prime are inverses. You guys done this? Yeah, because now when they invert it, you can tell you it's the same u, right?
wait, then.
That's it.
I think that I'm gonna.
Oh, good. So, is it start like this?
Yeah.
Okay.
Y x dot y.
Yeah.
Is equal to x dot y dash.
Equals x dot y dash.
Which is equal to u.
Oh, okay, so you just wrote them in one line
Yeah.
and use unique. So
And then so x dot y dash.
x dot. What do you say?
Y dot dash y dash.
Y dash.
Is equal to u dot y dash.
Is equal to u dot y. Yep.
Which is equal to u dash over y dash. And then it's also equal. So since x dash y x dot y is also equal to y dot x, then it's also.
Wait, what did you say?
So x dot y is equal to y dot x. So x dot y dash is equal to y dot x dot y dash.
Wait, hold on. Yes. Oh, am I writing that down? X dot y
Yeah.
is equal to.
Y dot x.
Oh, okay, yeah.
So x dot y dash is equal to
So x dot y dash
is
yeah.
equal to y dot is equal to y dot u.
Oh, okay, yes. Y dot x y dash, right?
Yeah. Is equal, yeah. Which is equal to
Y dot u.
y dot u.
Oh.
It's like
Right out of the text. Y dot u, yeah.
Y dot u. Which is equal to y.
Which is equal to y, yeah.
Yeah. So then y equals y dash.
wait, so for the associative one,
Yeah, because these are the same thing, yeah.
for associative one, it basically says that you can do it any of it in the same.
Yeah.
So if you put y dash dot x dot y
Y dash dot x dot y, yeah.
then you can just rearrange it and be y dot x dot y dash y yeah.
Oh, so you're basically saying use
Y dot y no just one. Yeah, you can do that with
yeah, so you're grouping it this way and that way, right?
Yeah. And then this is the both equal to u and
Oh, okay, so this is u dot y equals y dash dot u, yeah?
Yeah.
And then y equals y dash.
If you have like three things and then you're doing like an operation on, if it's associative, that means you can do the first and third one first.
Yeah.
But then wouldn't that like how does that write in terms of commutativity?
Oh, that's a good one, yeah. So maybe that's not true if it's not commutative. Let's see what you're trying to say. So maybe we can make that an exercise too.
Because I'm pretty sure if you can do the first one and third one, then it's not. Then it has to be a commutative.
Yeah.
Yeah.
That's a good one, yeah. So we're saying that yeah, because last time we proved that we did have commutativity too, right? So what are we trying to say? We're trying to say x dot y dot z, right?
Yeah.
May not be equal to, right?
Yeah.
X dot z. Yeah, because that's getting the z out of order. Yeah, that's a good point. I think you're right. Yeah, because it doesn't even make sense where to put the y now.
Yeah. Because then that's just commutative.
Yeah. We should come up with some examples of a non-commutative group. Yeah. So actually, I think a good example was the permutations one.
Oh, yeah.
That's probably the first
Yeah.
examples we can come up with. So like, can we see why it's not a commutative group first of all? Maybe we can even. So if you had permutations like 1, 2, 3. So maybe if we like name some permutations.
Oh, it's not even associative.
Oh no, it's associative.
Is it?
Yeah, because it's the same as composition of functions.
Oh, okay, yeah.
Let's see. What if we swap these two, right? Yeah. And then we swapped the second two. Like that.
Oh, yeah. So
Does that
it's
make
not
sense?
commutative. Yeah.
If
Oh,
we
the
so
example I'm doing, so
that
it's
makes
not
sense.
commutative.
if
Oh,
we
the example I'm doing.
so if we did the other way it'd be like this, right?
Oh yeah. Because this, yeah.
Um, 1 goes to 3 here, right? But 1 goes to 2 here. Yeah. So that's already interesting. Yeah, I don't know. I guess maybe I can just summarize. Can I say one thing before we go? So, actually, no, I won't. No, the next time. All right, that's good. Okay, so we have a first example of non-commutative group. Okay, and we're going to be interested in finite groups. Okay, finite groups.